it's Miss Therese here with our Intro to Kinetics video. So in this video, we are going to talk about what is kinetics, how to determine rate, why reactions happen, and factors that affect our reaction rates. So for this unit, what you're really going to need is two things. Number one, your calculator. There's a lot of math in kinetics. And then number two thing that you are definitely going to need is a periodic table. Now, guys, we're not really going to be looking so much at the elements on the periodic table, but you may want it for the references. All right, so let's jump in to kinetics. Okay, so our next three units are really kind of almost married. Not really, but they kind of merge and the topics kind of all have their own place. So our first unit that we're talking about today is kinetics, and kinetics is all about speed of a reaction. Next unit that we'll be doing after Christmas break is thermodynamics. So thermodynamics is energy of a reaction. How much energy does it take? And then finally, last but not least, the next unit after that will be equilibrium. And equilibrium is my reaction going to go to completion, or is it reactant or product heavy? Now, these three units kind of all three come together to let us know if a reaction is going to take place. So kinetics tells us, is it going to take place fast enough for us to actually see a reaction? Thermodynamics tells us, is this an energetically favorable reaction? And then equilibrium tells us, are we actually going to make products? All right, so those are kind of our three units that we're going to talk about. So thermodynamics, like I just said, tells us if a reaction can occur based on energy. Kinetics tells us how quickly the reaction occurs. So some reactions are, yes, thermodynamically favorable, energetically favorable, but they are kinetically so slow that we can't actually see them happening. And so I always think about this with like vinegar and baking soda. So when you add vinegar and baking soda together, it immediately like gushes up, you see that, and there's an immediate reaction. Versus with something like hydrogen peroxide, which most of you probably have at your house in your medicine cabinet, that is constantly breaking down, but it's a very slow reaction, and so it's not perceptible to us. But if we add a catalyst, it happens really quickly, and we're able to see the reaction. That's elephant toothpaste, guys. So even if it is thermodynamically favorable, kinetically, sometimes it's just a really, really slow reaction. Same thing with like diamonds. Diamonds degrade into over time, but it's such a slow reaction that we don't ever see it really happen. So we don't think that they are reacting, but they are. So with kinetics, what we're really going to be focusing on is rate of reaction. So how fast is our reaction? So let's start by defining that. So a reaction rate is the change in concentration of a reactant or product per unit time. Okay, so it is concentration. So concentration is kind of our amount there. And so we're going to say, sorry, I want to get the black ink. All right, so we want to look at our concentration. And concentration would be units of molarity. That's what those square brackets mean. So anytime you see those square brackets, we are talking about our molarity, which, if you remember, molarity is equal to moles divided by liters. Okay, and so our reaction rate can be of our reactant or of a product. Whenever we're talking about the reaction rate of a product, we are talking about the rate of appearance. All right, so rate of appearance is for products. All right, and it is equal to our change in concentration of our product over our change in time, whatever that is. Okay, so that would be our first one, would just be change in concentration of our product over change in time. However, if it adds a reactant, if it involves a reactant, we have a slightly different here. We have the rate of disappearance, all right? And this would be for a reactant. Now, guys, we have rate of appearance and rate of disappearance. What's going on there? Well, in our reactions, we are forming products. So we should start with 0 as our concentration and then form products. So the concentration of your product should increase. But of our reactants, we start with our reactants and they form those products, so the concentration of our reactants should go down. So our rate of disappearance should be negative our change in concentration over our change in temperature. The reason it's negative is because our concentration is decreasing. So as our concentration decreases, we still want to so since our concentration is decreasing, this gives us an overall positive value. But yeah, we have that negative there because our concentration should decrease. Now then, whenever we do solve these, this does give us the average rate, and that will be the average rate over time, but our rate doesn't stay the same because as you as you form more products, you have less reactants to react, so they're not going to react as quickly because there aren't as many reactants. So if we want to get an instantaneous rate, we actually have to use a graph. And to get that instantaneous rate, that rate at that moment, we are going to compute the slope of a line tangent to the curve at that point. So you'd basically figure out your tangent line. Remember to solve for slope. It is change in y over change in x. And that would give us the slope of our line there. And so our rate will be equal to the negative slope of the tangent line. Now, our rate of our reaction, like we talked about, is not a constant, but it will change over time because your concentrations change over time. So for the most part, what we're going to use in kinetics is we are going to use reaction rates that are initial. And we're going to say our reverse reaction is negligible. So what is a reverse reaction? So in a normal forward-moving reaction, reactants turn into products. In our reverse reaction, products turn back into reactants. Okay, so normal reaction, reactants turn into products, but in our reverse, products turn back into reactants. Okay, so now let's do a quick practice with our rates here. All right, so this one says, express the rate of reaction in terms of the change of concentration in each of the reactants and products. All right, so we're going to start with our reactants. All right, and our rate would be equal to the change in concentration of N2O all over the change in time. Now, since that is a reactant, it is going to be negative because our concentration of our reactants would decrease. Then our rate for nitrogen would once again be our change in concentration of nitrogen all over our change in time. And for oxygen, rate is equal to change in concentration of oxygen over change in time. Now, these rates are going to be different because we have different coefficients. So right here, since I have 2 moles of dinitrogen oxide for every 1 mole of oxygen, my rate of the consumption or my rate of disappearance of my dinitrogen monoxide is going to be twice or double the rate of like my formation of oxygen, since for every 2 moles that decomposes there, only 1 mole of oxygen forms. So our rates aren't going to be the same. And if it did ask you to write them the same, you'd have to use like your coefficients of your balanced equation to figure that out. So just to let you know. All right. So now we have a question, and our question says, in the first 15 seconds of a reaction, 0.15 moles of O2 is produced in a reaction vessel with a volume of 0.500 liters. What is the average rate of reaction during this time interval? All right, so our change in our reaction is going to be our change in time, change in our concentration over our change in time. So first thing we see here is this 15 seconds, and it says in the first 15 seconds. So I can take that 15 seconds to be my delta T. It says 0.15 moles of oxygen is produced in a reaction vessel with a volume of 0.5 liters. Okay, so once again, guys, this is a product, so it should have started with 0, and that means we ended with 0.15 moles. So we should have started with our concentration of oxygen at 0 in our reaction vessel. So our change in concentration is essentially just going to be how much did we form since we started with 0. Okay, But this is not concentration. It does give me everything I need to solve for concentration, but this is not concentration. So my molarity is equal to moles divided by liters. So I have 0.015 moles of O2 over 0.500 liters. So then plug that on into your calculator. And when I did that, I got 0.030 molar as my concentration. So then my rate is going to be equal to my change in concentration, which we started with 0 and we ended with 0.030. So that's my change, over my change in time. I am going to include my units here. All right, so then we'd plug that on into our equation. So 0.030 molar divided by 15 seconds. That kind of looks like a 5, but it is an S. And I got that our rate would be 0.0020 moles per liter per second. So remember, molarity is moles per liter there. So moles per liter per second. All right, and that would be our rate of our formation of oxygen. Now then, our next question says, predict the rate of change in the concentration of N2O2 during this time interval. In other words, what is our rate of N2O2 over delta T? Okay, guys, so this is where we would use the coefficients of our balanced equation. All right, so I know that my rate is going to be equal, of that one, is equal to negative delta change in N2O over change in temperature. Okay, guys, well, I know for every 2 moles consumed, it's going to make 1 mole of oxygen. So that means that basically, if I compare it to my rate of oxygen formed, it's going to be 2 times my change in concentration of oxygen over my change in time. It's going to be 2 times that because for every 2 moles I use there, I make 1 mole of oxygen. So my rate of oxygen is going to be doubled in order to be equal to that one. So basically multiply your rate of oxygen by 2, and you get that your rate would be 0.0040 moles per liter per second. And that would be our rate of disappearance of our reactant. All right? Okay. So now we're going to talk about collision theory. All right, guys, and collision theory is kind of our explanation for why chemical reactions occur. Now, this video is a TED Talk, and it's really a great explanation, and it just gives a really good analogy. So what I want you guys to do right now is to go pause this video, click that link, and watch that TED Talk. It's 6 minutes long, so click that link, watch that TED Talk, and then come on back here so that we can talk through the rest of our notes that really follow along really well with that video and the topics discussed there. All right, so pause it and go watch the TED Talk. Okay, hopefully you did that and you paused it and you watched the video. So now we're going to go through and kind of talk about collision theory. Okay, so collision theory is basically the theory of how reactions occur, all right? And we say in collision theory that molecules must collide in order to have a reaction. Now, a lot of molecules collide, but only a small portion of those collisions actually produce a reaction. So based purely on the number of collisions, our reaction rate is much smaller than we would totally believe. And that's because there's really 2 factors that are important in those collisions. Those collisions, number 1, the molecules must collide, but they must have the proper amount of energy for a reaction to actually take place, and they must be properly oriented. So our molecules must be turned the right way so that when they hit, they are able to react. All right, so they have to have the proper energy and they have to have the correct orientation. That's collision theory. So molecules must collide with proper energy and proper orientation. All right. So now let's talk about how can we affect reactant rates. So how can we affect or speed up or increase the rate of our reaction, especially if some reactions are thermodynamically feasibly, but they're kinetically so slow. There's really 5 things, but there's 4 main ones that we're going to talk about. And the first one is concentration of reactants. So higher reactant concentrations increases the reactant rate because if we have more molecules, there's more collisions. The more collisions you have, the more likely it is that those collisions are going to have the proper orientation and the proper energy in order for our reaction to take place. So higher concentration, more molecules means more collisions. Next is surface area. So smaller particles have more surface area, and that increases our rate because our collisions are going to increase. So the more surface area you have, the more likely you are to be able to have a collision. Oh my goodness. Lucy has decided to join us on the table. All right. The more likely you are to have a collision. Next is temperature. So increasing temperature is going to cause our particles to move more, which gives them more energy, which means they are more likely to have that sufficient energy in order for our reaction to take place. But beyond just having that sufficient energy, it also means that our molecules are moving faster, so they're going to they're again going to be more likely to have those collisions. This is kind of interesting, but our rate often doubles for every 10 degrees that we increase in temperature. So as temperature increases, more collisions are going to have that sufficient energy to overcome the activation energy. And yeah, as temperature doubles, the amount of the reaction speed it's exponentially greater than it was before. So temperature. And then the last of our main ones is catalysts. So catalysts also can increase the rate of a chemical reaction. Now, they increase it by lowering the activation energy. So activation energy is the energy that we must overcome to produce a chemical reaction. So our reaction rate is really dependent on that activation energy, not what you would think, which is the change in energy, or delta H. Delta H is our enthalpy. If you don't remember, that's what we're going to talk about last year. But change in energy is basically the difference in the potential energy of your reactants and your products in a chemical reaction. So delta H actually does not have any effect on the rate of the reaction, but your activation energy is what affects it. So the higher the EA, the more activation energy your reaction has, the slower it's going to be, your reaction's going to be. So endothermic, exothermic reactions, it doesn't matter. Even if it requires energy, it's all about that activation energy. So endothermic, if you guys remember, is one where it requires energy for the reaction to start. Exothermic does release energy, but you'll see we've still got that activation energy on both of them that requires our reaction to take, that our reaction has to have in order to take place. So what do catalysts do? Catalysts, they speed up a reaction without being consumed. So they are not used in the reaction. And they produce a new reaction pathway with a lower activation energy. So catalysts act in different ways. They can either change the mechanism, or they can just be a place where the reaction takes place so the molecules are oriented properly. Sometimes they will help react, create an intermediate, and then that intermediate is consumed later. But yeah, so catalysts change the mechanism, there you go, or they just change the rate determining step somehow. So that's what catalysts do. You can see right here in this graph shows our uncatalyzed pathway versus the catalyzed pathway. So our catalyzed pathway is going to have a significantly lower activation energy, which is going to make our reaction much more likely to occur. So we do have different types of catalysts as well. We have enzymes, which are biological catalysts. This is what's in your body. This is actually what the majority of the reactions that take place in your body do require a catalyst to happen. So you definitely need catalysts in your body. Then we have a homogeneous catalyst. All that means is that it is present in the same phase as the reacting molecules. So if our reaction is in liquid phase, our catalyst would be in liquid phase as well. And then heterogeneous catalyst exists in a different phase. Typically what this is a gaseous reactants being absorbed on the surface of a solid catalyst. So yeah. So typically what happens here is a new reaction intermediate is formed, or the probability of collisions is increased. This also can be called a surface catalyst. So our last question is, how does the mechanism for the catalyzed reaction differ from the mechanism of the uncatalyzed reaction? And this is kind of what it shows us. So our activation energy with a catalyst, we see that it is lowered, but a lot of times what happens in a catalyzed reaction is it's changing our reaction pathway. So reactions actually happen stepwise. They don't all happen just like at once. So I don't pour like vinegar and baking soda together and necessarily immediately get my products, but sometimes it happens through steps. They happen pretty quickly, so we don't always see those steps, but they do still happen through steps. So it's kind of like if you think about getting a sandwich, if I say I'm going to go make a sandwich, that means I'm not just like going to go into the kitchen and a sandwich is going to magically appear, but there's steps I take to make that sandwich. So I have to get bread, I have to get mustard, to put it all together, like whatever. And so there's steps that go through. So it's the same with chemical reactions. So sometimes there are steps that our reaction goes through before we actually see the end. And so what will happen in those stepwise reactions is that basically our catalyst is sometimes they basically lower the activation energy of those steps a lot of times. So with our catalyst, our hump is a lot lower, and it makes those stepwise. It oftentimes affects the rate determining step, which our rate determining step is our slow step, or the one that is going to be kinetically slower. And so our catalyst is going to basically lower the activation energy of that and just make it easier for our reaction to take place. Okay. So for today, you guys definitely have a kinetics POGL that we want you guys to work through. It's kind of an intro to kinetics. It will be due next class, but feel free to email Mr. Oglesby or myself if you have questions. All right, guys, have a good night or day, whatever it is. All right, bye, guys.